Hello, R fans. Welcome back. And this is module 10 of multivariate statistics. And I'm excited. This is one of my favorite topics. We're going to talk this week about confirmatory factor analysis. And that means we are getting into latent variable modeling, which is a very cool sort of subfield area of statistics that is amazingly flexible and allows you to do lots of really neat things. So we are working on here on the module 10 R markdown file. There's a handout already available for you on Canvas. This code is also there. And the data set, which is actually the same data set that we used last week for exploratory factor analysis. So this is the SAQ data set, Andy Field's statistics anxiety questionnaire. So we're going to load in some packages. Two of these are very familiar and two are not. So the two that are familiar are Tidyverse and Haven. Tidyverse is our go-to for all things data management. Haven is useful for importing data sets of any type from other statistical packages into R. Lavaan is the go-to for all things SEM. So this is a new one. Lavaan stands for latent, L-A, variable, V-A, analysis, A-N. It is an open source R package, just like all the others. It has a ton of flexibility. It's very well developed and supported. I like it a lot, and it's very useful for our purposes. And then this library SEM plot creates some really cool path diagrams for SEM models, not unlike the path diagrams that you saw last week when we did exploratory factor analysis. So this is just sort of an extension of the same kind of approach that we used last week in EFA, using a different package to create those path diagrams, which I think is pretty cool too. So let's load in the SAQ data. And that's, again, just using the read DTA function, which by now should be pretty familiar. And then we glimpse this. And again, this is 23 questions. So this is just basically a survey instrument. All of them are Likert type questions, running from 1 strongly disagree to 5 strongly agree, I believe. And we have 23 items. If you remember last week, we found that only one of these items was actually written in the opposite valence. Remember, items can have a positive or a negative valence. And we discovered that question 3 actually is written in a positive way, while the other items are written in a negative way about statistics. And so we need to recode that item 3. So this code here, starting in line 21, is essentially exactly the same as the code that we used last week. So first of all, we create a new variable called question 3R because it's reverse coded. And that is just equal to 6 minus question 3. And the reason we choose 6 is the little trick we learned last week, right? Which is if you need to reverse code an item, a survey item, you subtract 1 more than the top range of that item minus each individual response. So in this case, since the top range is 5, we subtract 6 minus all those other responses. And then we're just using the select function, and we're negative selecting, right? We're selecting out the old question 3. So we're only left with the new reverse quoted question 3. And we can double check that item there. So we should have the same number of variables. We do, because we've just added a variable and taken one away. And then we can also glimpse this new item to make sure the coding worked. So the first 4 responses are 2, 2, 4, 5. So that means that the first responses on the original item should be, let's go up here to the original item, 4, 4, 2, 1. That's right. So 2s translate to 4s, 4s translate to 2s, 1s translate to 5s, just the opposite of the transformation there. Okay, so now that's all the setup work we need to do this week. From here, we can sort of take it to actually running some CFA models. Now let's talk really briefly about how this might work in your own research. So we learned last week how to do exploratory factor analysis, and we had a set of data, this same data set, and we ran an EFA, and we figured out that there were basically, I can't remember, four or five different subscales or latent factors within that instrument. So when we looked at that Andy Fields instrument, statistics anxiety actually covers a lot of separate but related concepts. Remember, we used the Promax rotation that seemed to work pretty well. So those things are allowed to correlate with each other, those latent factors. So now, typically, when you're developing an instrument, the next step is to move into CFA, or confirmatory factor analysis. This is usually conducted on a separate sample. So just want to make that note. Here, we are using the same data to perform EFA and CFA. That's generally not advised. Actually, our data set is big enough, we might even be able to randomly select. So we might be able to take one random half of this data set and do an EFA, and then the other random half of the data set and do a CFA. That's that's called a split sample approach, and that works pretty well if you have a lot of data. If you don't have a lot of data, then it typically means collecting data twice, one at the EFA stage and one at the CFA stage. But this is, of course, part of a larger body of research, right? This isn't all one study. The first step is sort of the EFA. Does this have some initial evidence that it holds together very well? And then the CFA is really much more about the measurement, much more precise, identifying those subscales and getting clean estimates of all those items. So anyway, that's just a little context as to when you would do EFA versus CFA. So let's say that we were really interested in the subscale that we called computers in the Andy Field data set. So this is the set of items that all have to do with anxiety around using a computer, or SPSS, to do statistics. So that's questions 6, 7, 10, 12, 13, 14, 15, and 18. And that roughly lines up with the results of our EFA when we look to see what that all these items sort of load together pretty well. So let's say we want to do a CFA just for the computer scale. So we're ignoring the other items for the moment, and we're looking just at the computer scale. Okay, so the first thing that we need to do is to create a written version of the model that the software is going to interpret from the words and put it into an actual statistical model. And the way you do this is just by defining a string of text right here. So I call this computers CFA 1 because this is my first computers CFA model. And what you do is you put the model inside of single quotation marks, like I've done here, not double quotation marks, but single. So notice if it's double, it turned from green back to white. Now you're, depending on what color setup you have on your computer, it may not be green, but whatever the color is for text is going to change colors here. So this is a single quotation mark at the beginning and a single quotation mark at the end. And the format is the latent variable goes first, the variable you're defining, the factor, right? So in this case, it's computers. And then you have this little operator here, which is an equal sign and a tilde right next to each other. So the tilde is the key that's right below escape on your keyboard. So if you look for escape, you'll find the tilde. And you might, think you have to hold down shift too to get that to actually work. So this is a very specific assignment operator, specific to lavaan, that lets lavaan know that you want to define a latent variable composed of the following items. And then you just list those items separated by pluses, almost like an equation. This item plus this item plus this item. So the whole thing is just computers is defined as a latent variable composed of these items, 6, 7, 10, 12, 13, 14, 15, 18, okay? And the whole thing is enclosed in single quotation marks to sort of set it aside, and it's green. So if you run this whole line right here, so if I highlight this and I go to run selected line, I now have something called a value stored in R. And that's just a string of text that lavaan is going to pull in, and it's going to manipulate to create the statistical model. So there it is. You can see it under values. Okay. So once we've defined the text of the model, we can actually run the model itself. And so what I usually do is, this is probably a good convention, I use the same name as the written model, and I just add model on the end. This is the actual statistical model that accompanies this equation. And so this computer CFA1 model is just a CFA, that's the command. Of course, you need to install lavaan and have that running. So if you don't have that, it won't recognize that command. And then you list the name of the model that you're using, computer CFA1, and then you tell it where the data are. In this case, saq.clean. And that's it. It'll run that CFA model. And then underneath that, here, I can run that line just so you see what that looks like. So that stores a lavaan object up here in your environment. So those are the results and everything else. And then to get the results out, you just run the summary command. We've done that before with other types of models, and it prints out the results to your console. So there you go. One thing you'll realize with CFA models and all latent variable models in general is that you get a ton of output. This is very common. It happens in all the software. The output is like, because latent variable models estimate everything unless told to otherwise do so. And so you get variances, you get slope estimates, you get intercepts. A lot of it we don't necessarily need, but it's there just because that's sort of the environment in the latent variable environment. So you get this little message here. This is good. lavaan version 0.6 ended normally after 20 iterations. That means that a stable solution was reached. We didn't have an issue with model convergence. That's good. The estimator here is what's called ML. So that's maximum likelihood. That's great. The optimization method, we don't need to worry about that. You're welcome to read more about the optimizer that's used, but it's pretty technical. Number of free parameters is 16. So that is the number of data points minus the number of parameters being estimated. So that's the formula that we actually calculated in the lecture, if you remember. So that's how you get 16, is you take the number of data points minus the number of parameters that are being estimated. And not data points as in sample size, but data points as in how many variables are in the model times, I think it's the number of variables plus 1 or something like that, and then minus what we're estimating. Number of observations, 2,571. Then we get a chi-square test statistic where it says model test user model. So 253.85, that is the chi-square that is associated with this model. And we had 20 degrees of freedom, and then we get a p-value for that chi-square. Now, ideally, that's the thing that we would want to be statistically significant. In this case, it's not, which is totally fine. Again, in large samples, and this is definitely a large sample, that test tends to be statistically significant too often. It's overpowered. And so it's not unusual to see a significant chi-square, but that's where the chi-square is. That's where the kind of the most important model fit measure is. Then we get some information about types of standard errors and the approach to obtain the parameter estimates. Then we get our latent variables that we estimated. We only estimated one, which was computers. And so these are factor loadings. So here is question 6, 7, 10, 12, 13, 14, 15, and 18. And these are the factor loadings associated with those. And so what we want to find, hopefully, is that these are fairly close to each other, fairly similar. Now, in this case, question 10 has quite a bit lower loading than the other items. So it seems that question 10 doesn't fit quite as well on this scale as the others. That doesn't mean it's a bad thing. We should get rid of it, but it just doesn't fit quite as well. And notice here, question 6 has an estimate of 1, and it has no standard error or test statistic. So what that tells you is the computer has fixed item number 6 to have a loading of 1. And this is called the, I think it's called the marker approach, the item marker approach for giving your latent variable a scale, because that's an issue. And we talked about that in the lecture as well. You can either fix the variance of the latent variable to 1, or you can fix the variance, or you can fix the loading of one of the items to 1. In this case, they've used the marker approach here. When we want to get standardized estimates, which we'll get in a moment, we will actually fix the variance of the random variable, of the latent variable to 1, which will give us standardized estimates for all these items, which is generally preferred. Here are the variances. And notice there's just a little dot put in front. So these are the error variances. So each little item has its own specific error term, which is really cool. So it's a very specific structure of the error. Unlike, for example, when you create a scale, by taking the mean or Cronbach's alpha, you make a lot of other assumptions about the underlying data. Here, we assume that each item has its own error, unique error, and we estimate that. Particularly, we estimate the variance. And so higher variance, since all these variables are measured on the same scale, variables with higher variance generally mean they're not as strong contributors to the latent factor. Although here it looks like there's pretty good, pretty consistent contribution across the board. Question 18 has a lower error variance, which means more of its variation is contributing to the latent variable. Variables, questions 6 and 15 tend to have higher, but generally we don't spend a whole lot of time looking at the error variances, at least in a basic CFA model. Okay, we can also, and this just gives you a little bit more information about how to not use the marker method, but how to fix the latent variable to 1 if you want to. We're not going to cover that in class. We're just going to use this standardized option, which also works very well. We can also create a path diagram of this model, which I highly recommend. So the command there is SEM paths. And you do need to specify here, just as I've specified it, this is called lazy loading. So for some reason, when I coded this out on my machine, I did need to tell the computer to use SEM plot. So SEM plot, : SEM paths, and then you put the name of the model. Remember, not the text, not this part, but the actual name of the model. And then under what labels you put est or estimates. So all you would need to do is change the name of your model and you'll get a cool path diagram. So this is it. It's pretty cool. So here we can tell with a dotted line, this is the loading on item number 6. It's been fixed to 1. And here are the other item loadings, 1.02, 0.5, 0.7, 0.9, so, and so forth. These squares, of course, are observed variables. So these are the actual items that comprise the latent factor. And these are the error variances, the little kind of like horseshoe things. And this is the error variance of the latent variable, which in this case is estimated to be 0.5. And it even puts 3 letters in the circle for you to tell you that this is the computer's latent factor. And notice that the latent variable here is a circle as opposed to a square. So you just estimated your first latent variable model. This is a CFA model for computers using 7 or 8 indicators. Okay, so I mentioned this before, but you may also want to obtain standardized estimates. It's usually a good idea. And so basically you run this same summary command that I ran way up here, but you add a couple options. And these options I almost always leave on. So this is kind of the standard format that I run whenever I run a CFA model. So fit.measures equals true and standardized equals true. Now, if you remember, when we looked up above, the only fit statistic we got from our output was the chi-square. And that's fine. It's a very important fit measure, but there also are other fit statistics that we learned about in the lecture that we would want to get. And so fit.measures equals true adds those in and calculates those. And then standardized equals true gives us our standardized estimates, which are generally, I think, a little bit easier to interpret. So just like that, it runs. So here's our chi-square. We talked about that before. And then, so it's interesting. So we get an additional test here, which is a model test of the baseline model. And what the baseline model is that essentially all items are just correlated with each other. So there isn't that kind of latent connection. They're all just sort of correlated. And in this case, we see a significant improvement from the baseline model, which is has a chi-square of 6309, all the way down to a chi-square of 253. So we reduced our chi-square by more than 6,000 points. That's huge. That's really good. And that shows evidence of significant model improvement. We also get our CFI and TLI. The comparisons here are 0.95 is what we're looking for. So these both look pretty good. We get our AIC and BIC and sample adjusted BIC. So these are sort of global measures of fit. So if you change your model somewhat, you can sort of compare changes here. We do that more in something like multi-level modeling or some of the other latent approaches. We wouldn't use that as much in CFA. In CFA, we kind of look at these fit statistics. And then we get our RMSEA. So what we're looking for here is ideally below 0.06. Some people say 0.08, just kind of depends. Our estimate is 0.067, so that's not bad, kind of on the border. And then we get the confidence interval. So the low range of this is 0.06. The high range is 0.075. And then we get a p-value for whether or not the RMSEA is actually below 0.05. The null hypothesis is that it is. In this case, it's significant, so we would reject that. So ideally, this is non-significant, and the confidence interval falls completely below 0.06, but that doesn't appear to be the case here. Then we get our standardized root mean square residual, or SRMR, and that I think is 0.06 is again the cutoff, or maybe 0.08. It's 0.03, so that looks pretty good. Then we get the estimates of our latent variables and our variances, but notice two columns have been added. So there's std.lv and std.all. So std.lv uses what's called a latent variable standardization, and std.all, that's generally the one I use, provides standardized estimates for all of the items. And so now we can compare these as like more traditional factor loadings. So question 6 has a loading of 0.66, 0.68, 0.4, 0.6. And generally the cutoff is like, 0.3 or 0.4. So question 10 is pretty close. I would want to really look at that question and see if maybe it might be dropped. But the others appear to have pretty good, strong, consistent loadings. Question 15 also is a little bit lower, but not too bad. And then we get standardized estimates of our variances as well. And you can see down here, the estimate of computers, the variance has been fixed to 1. If we want to get standardized estimates, it's very easy. It's the same in a path diagram. It's the same command, except for what labels we put in stand for standardized. And now we have our standardized estimates. And notice that the variance of the random variable is fixed to 1, which is what we want. Okay, so let me check my time, see how long I've been going. This is probably a good place to stop. And then, actually, let's do one more. Let's do this, adding one more item, and then we'll come back and do a part 2. So let's say there was another item that we were considering for this scale, but we didn't have great evidence as to whether or not we should include it. And here we're going to add in question 23. Now, spoiler alert, question 23 does not have to do with computers. It's about, I think it's about friends. And so here I'm sort of intentionally showing you what happens when you add an item that doesn't work well with your latent factor, just to kind of demonstrate what it looks like. But you could also do this sort of intentionally with another item that you thought might fit. The process is very similar. We're going to call this computers CFA 2. This is our second computer CFA model. And again, in single quotation marks, we've defined this whole model. And all I've done is I've added this part right here. I've added item 23. So now I'm changing how the latent variable is parameterized. I've added an additional variable there, an item that I think also contributes to that latent variable. And then I run the model here. Again, the command, I've added model on the end. It's still computer CFA 2, and it uses the CFA command. And then I get the summary of that model, and I get my fit measures, and I get my standardized estimates. So I'm going to run all of this at once. This is what I typically do with latent variables. I define the model, I run it, and I get estimates all at once. So this is our new model. This is our 9 indicator model with one indicator that we know is crummy. So if I'm looking here, so right off the bat, I've added a variable here, but it looks like the chi-square went up slightly. Now that's not directly comparable because it's not, I've added a variable, but that's still not a great sign. And my CFI and my TLI actually don't look too bad, 0.96 and 0.95. And my RMSEA also doesn't look too bad either. So that's interesting. Now I'm questioning myself. This may have actually been a good, maybe a good item that I'm adding. I thought I picked one that was bad. And then, so my RMSEA now is at 0.058, and the 90% confidence interval goes from 0.05 to 0.06, and the p-value is better too. It's not non-significant, but it's close. And the SRMR is better. So boy, I think I added a computer item here, folks. I don't think I added an intentionally bad item. Let's look at the model fit here. Oh no, actually it's not that good, right? It doesn't fit all that well. The factor loading here is negative. That's not a good sign. And it's quite low at 0.1. And when you look at it in terms of standardized estimates, it's also not so great. So in terms of global fit, this actually fits pretty well. But this factor loading is really, really crummy because this is intentionally an item that doesn't fit with the idea of computers. So I would want to go back and notice the variance of this thing is very, very high as well. I would want to go back and get rid of this item, not necessarily because it results in bad model fit, because the fit actually looks pretty decent, but because the loading of this thing is just so crummy. I would want to kick that out. Because generally you want all your items to load at 0.4 or above is kind of the cutoff. And this is well below that with a loading of less than 0.1 and even negative, which means it's kind of going in the opposite direction. Okay, so that's what happens when you try and add a different item. You get different fit statistics, and you can also examine those factor loadings. In part 2 of this video to come next, we will talk about the friends subscale. And we'll visualize that, and then we'll look at models that have more than one latent factor, combining subscales, and then we'll look at the whole thing and talk about modification indices. So lots of good stuff to come in part 2. Talk soon.